Hello everyone. So today our discussion will be on black body radiations. In our previous last tutorial video, we have discussed about the wave nature of electromagnetic radiations. So we have discussed about the wave nature, but electromagnetic radiation, okay, does not only possess wave nature but also particle nature. So today our discussion will be on black body radiations. So before going to the black body radiations, we will talk something on hot objects. So when we heat an object, okay, at higher or very high temperature, okay, they emit electromagnetic radiations, okay, of a wide range of wavelength. So at higher temperature, an appreciable proportion of radiation is in the visible spectrum. So suppose iron rod. So iron rod is heated at high temperature, okay, and after some time what we observe is it changes its color to red color at higher temperature, and still further on heating it changes its color to blue, and this range of wavelength, okay, is visible in the spectrum, okay. So we this spectrum is in the visible region, so we see the red and blue color, okay. When we heat iron rod at higher temperature and still on further heating at higher temperature, we see blue color, okay. So hot object, okay, example iron, they emit radiations, okay, and after reaching certain temperature, okay, this radiation is visible in the visible region and we see the red and blue color. So we can say this intensity, okay, intensity of radiation of different so this intensity of radiations of different wavelengths emitted by hot body depends on temperature, okay. So at different intensity they will show different color. So object made of different materials, okay, exhibit or emit different amount of radiations, okay. So when the surface of an object is irradiated, okay, some are reflected, okay, some are absorbed, and some are transmitted. So when an object is irradiated by light, okay, some are reflected back, and some are absorbed, and some are transmitted. Now a black body, okay. So what is a black body? A black body is an idle body which emits and absorbs radiations of all frequencies uniformly. So a black body is an idle body which emits and absorbs radiations of all frequencies uniformly. So the radiations okay, emitted by a black body, okay, black body is called black body radiation. So however, in reality no such object is observed, okay. So one example is a black carbon. So black carbon exhibit behavior, okay, closely related to a black body, okay, but however it is not a pure black body, but it is fairly close to a black body. So let us see a graph, intensity versus wavelength. So at a given temperature, okay, it was seen that the intensity of radiation, okay, emitted increase with increase of wavelength and start decreasing with further increase of wavelength. So these radiations, okay, at certain intensity reaches a maximum point or alpha max, okay, and decreases. However, this intensity does not increase continuously, okay. If we look at the perspective of theory, okay, the intensity wavelength relationship, okay, with the increase of wavelength, okay, the intensity should increase, okay, according to theory, should increase. Look, it should increase, go on increasing, but experimental data shows that the intensity, okay, increases up to a point and then decreases, okay. So it is not continuous. So this could not explain the intensity of radiation as a function of wavelength. So Planck suggests that atoms and molecules could emit or absorb energy only. Okay, so atoms or molecule could emit or absorb energy, okay, in discrete quantities and not in a continuous manner. Okay, so atom or molecule or energy, okay, atom or molecule, okay, they emit or absorb energy, okay, in discrete quantities. Discrete quantities means a fixed value or fixed quantity, okay, and not in a continuous manner, okay, not in a continuous manner. So he gave the name quantum to the smallest quantity of energy that can be emitted or absorbed. So that can be emitted or absorbed, okay, in the form of electromagnetic radiation. So the energy, okay, we call that energy as quantum, okay, that energy as quantum, which can be emitted or absorbed. So the energy, let us take it as E of a quantum radiation is proportional, okay, to its frequency nu, and is given by E is equal to h nu. So where h is Planck constant and nu is frequency, or we can write it as E is equal to n nu, where n is an integer and it can have value 0, 1, 2, 3, okay. H 2, 1 H nu, 3 H nu, and so on. This h is Planck constant, so the value of h is 6 into 6.2 to 10 to the power minus 34 joules second. So the minimum energy, you call that as quantum, okay. This energy have value hv, okay. So this energy, okay, is an integral multiple of this one, 1, 2, 3, okay. So a photon or can have energy, okay, hv, h nu, sorry. So this minimum energy, okay, this minimum energy is called quantum. So with this we can conclude that electromagnetic radiation, okay, electromagnetic radiation should have particles like nature, okay. So they should have particles like nature to be quantized. Quantized means they have fixed value of energy, okay. So they can have either hv value of energy, 1 hv or 2 h h nu, okay, or 3 h nu value, okay. So their energy is fixed or quantized. So as we have discussed earlier, a black body, okay, a black body is an idle body, okay. So this body is supposed to absorb all radiations when heated, okay, and expect to give all radiation, okay, out. Our next topic is photoelectric effect. So this photoelectric effect, okay, was explained by Hertz in 1887. Okay, so through his experiments, okay, he gave the phenomena of photoelectric effect. So in his experiment, he's taken a metal surface, okay, example potassium, rubidium, cesium, okay. So in his experiment, what he did was, so he placed a metal, okay, inside this vacuum or glass, okay, and then expose this metal surface, okay, by a light source, and this light gets reflected, okay, and through these experiments, what he observed was electrons, okay, electrons were ejected from the metal surface and was detected by the detector, which is a positive plate. So when light, okay, light pass through this metal surface, okay, so this light is carrying certain energy, okay, as we have discussed earlier, h nu, okay, heat the surface and electron is ejected. So this phenomenon, we call it as photoelectric effect. After this experiment, what he observed was the electrons, okay, the electrons are ejected from the metal surface as soon as the beam of light strikes the surface, okay, as soon as the beam of light strikes the surface, okay, the electrons were ejected out, okay, and there was no time lag, okay, no time lag between the striking of light beam and the ejection, okay. The number of electrons ejected, okay, number of electrons ejected is proportional to the intensity or brightness of light, okay. So the number of electrons ejected is proportional to the intensity, okay, or brightness of light. So more the intensity or more the brightness, more the number of electrons were ejected, and less, okay, or weaker the brightness of light, that means less number of electrons were ejected from the metal surface. For each metal there is a characteristic minimum frequency, okay. So for each metal there is a minimum frequency known as V0, okay, or we call it as threshold frequency, below which photoelectric effect, okay, photoelectric effect is not observed. So the nu O, okay, nu naught is the minimum frequency, okay, minimum frequency, and below this frequency, photoelectric effect is not observed. So if V is smaller than nu is smaller than nu naught, no photoelectric effect will be observed, okay. So a minimum intensity, okay, or energy, okay, smaller than the this threshold energy will not show photoelectric effect. At frequency higher than nu naught, okay, the ejected electrons come out with certain kinetic energy. Okay, so when this frequency is higher, okay, frequency of the light is higher than the threshold frequency, the electrons are ejected at a certain kinetic energy. Okay, so the kinetic energy written in short form of these electrons increase with increase of frequency of light use. So if we increase the frequency of the light, okay, the kinetic energy will also increase. Okay, that was what he observed through his experiment. Okay, so we have discussed that electrons ejected depend on brightness. The number of electrons ejected depends on the brightness. Okay, brightness of the beam of light, but not kinetic energy. But kinetic energy does not depend on the brightness of the beam. Okay, but depend on, okay, this kinetic energy depend on intensity or frequency. So how high the intensity or how high the frequency is, okay, that will result in higher kinetic energy of the electrons. An example: red light of any brightness on potassium metal does not show photoelectric effect. Okay, so red light of any brightness, okay, it can be weak, okay, or the brightness can be very high, but no photoelectric effect was observed on potassium when that red light was passed, okay, of any brightness. But weak yellow light on potassium metals result in photoelectric effect. So weak yellow light, okay, so by weak we know, okay, that means the brightness is not high. So a weak yellow light on potassium metals result in photoelectric effect. Okay, so the value of nu is given for red light 4.3 to 4.6 into 10 to the power 14 hertz, and for weak yellow light 5.1 to 5.2 into 10 to the power 14 hertz. So the minimum frequency of the potassium, okay, potassium metal is 5 point. So this minimum nu should be greater than v naught, nu naught. That means yellow light have higher nu, okay, frequency than potassium metal. So for kinetic energy, it depends on the intensity of frequency, not on the brightness. So Einstein, okay, Einstein gave a value, okay, gave the value of kinetic energy of electrons, okay. He gave the kinetic energy of electrons h nu h. He gave the kinetic, okay, value of kinetic energy of electrons, okay, h Planck constant h nu naught plus 1 by 2 me v square. So we know that every photon has energy equal to h nu, okay, and minimum energy is h nu naught, okay, and then plus the kinetic energy, okay. This is the kinetic energy. So these relations give the kinetic energy of ejected electrons, okay, ejected. And here me is mass of electron, nu is v here is velocity of ejected electron. So remember this relation, okay, for calculations and all, and remember the Planck constant value also, okay, for calculations.